All right, let's look more at some of the components you're going to see on a ISO schematic. So the general shapes that we're going to be using to identify different types of components are going to be squares. Squares are generally going to represent valves. So if there's like a relief valve we'll see here in a little bit, it's going to be inside a square. Directional control valves, if there's multiple positions to them, like extend, neutral, and retract, you would have three boxes or three squares all attached, indicating each different position that that valve can be placed in. Another uh, shape indicator that we're going to see is going to be circles, which are going to be indicating either pumps or motors. So inside the circles, as we're going to see here in a little bit, there's going to be arrows inside, either pointing out or pointing in, indicating it's either a pump pushing oil out or a motor that's taking oil in. Diamond shapes down here are going to represent fluid conditioners. Now, by a fluid conditioner, what I mean is hydraulic oil coolers. They're changing the temperature of the oil, so it's changing the condition of the oil, as well as filters is another popular one. Filters they filter the oil, so they change the actual components in the oil. So they are a fluid conditioner. Springs are going to be represented by this shape here, which looks like a spring. The next one down here is a diagonal arrow. If we ever have a diagonal arrow across a component, that means that that component is adjustable. For example, if I took this spring and I put this arrow and I put this arrow across a spring like that, that would now indicate that that spring is adjustable. I can change the tension on that spring. Next thing down here is just a solid black arrow. That's going to indicate the direction at which the oil is flowing. A lot of times you'll see those arrows inside different components that tell us which way the oil is flowing inside that component. Moving along to the next next components we're going to see. Reservoirs. So reservoirs are going to be indicated by either an open U shape like this or a closed in shape like this. Now, if it's an open U shape, that indicates it is a vented reservoir. So it's non-pressurized. Most of the reservoirs in our industry are vented, so they would be open like this. There's some exceptions that we would have a pressurized reservoir, such as on some sprayers. We would see a pressurized reservoir. Now, when you have reservoirs on a schematic, it's not just going to be one reservoir and all the lines have to go back to that reservoir. That would make the schematic look really busy and it would be a big mess because you'd have a lot of return lines going across a whole bunch of different components, which would really clutter it up. So what we do is we'll just have reservoirs located all over the schematic. Now that doesn't mean that there is multiple reservoirs on the machine. It just is, we do that just for clarity. So the example down here where we have a pump, it's sucking oil out of a reservoir and then pumping oil back into a reservoir. This reservoir is the same one. They're just indicated by two different symbols, but it is this same housing. So moving on to pumps. Pumps can be fixed displacement or variable displacement. There's that diagonal arrow I was talking about a little while ago. Fixed displacement pump, again, is a circle with an arrow pointing out. As soon as we put a diagonal arrow across it, now that pump, it's adjustable. It is variable pump, variable displacement. This one here, now we have a pump that is variable displacement, and if we have a little line coming off the side here, that's just indicating a case drain line. So a lot of times you would have a reservoir that would be connected to that little case drain line. Going down here to the middle, this pump here is going to be a bidirectional variable displacement pump. So because it has two arrows, that means this pump is bidirectional. Now that doesn't mean that the pump can spin clockwise or counterclockwise, but it means it can pump oil out one port or the other. So what we do there is inside the pump itself, there would be a swash plate that would go over center and then go in the opposite direction. So again, we don't stop the pump and spin it backwards mechanically. It's always spinning in the same direction mechanically. We just inside the pump can switch which port is going to be our inlet and which one is going to be our outlet. Over on this one here, the only difference between this one that's labeled mechanical connection and the bidirectional variable displacement is this symbol here happens to show an actual mechanical connection. Not every schematic does that, and we know just by working in the industry, our pumps are generally all driven mechanically. They're usually all gear driven off of the transmission or the engine. So we know they're driven mechanically, but some manufacturers will actually draw the mechanical drive shaft, and they might show you exactly or what's running it. They might have a picture of the engine or a box that's labeled engine, so you know it's an engine driven pump, or they could have it on gears inside a gearbox and a transmission, indicating that the pump is driven off of the transmission. Nonetheless, anytime you have this double line and symbol on the side of this pump, that double line is going to indicate a mechanical connection. We're going to see that double line coming back again when we get into other directional control valves. We're going to see other mechanical connections look the same way. So just take note of that. So these are all pumps. These are the inputs into our hydraulic system. So next thing let's go over is some actuators. Now at the end of the day, we use hydraulics either to turn a motor or extend or retract a cylinder. That's really all we're trying to do, is either turn a load in a rotary fashion or a linear fashion with a motor or a cylinder. There is, just like pumps, there's different types of motors. We can have a unidirectional motor, which means this motor only spins in one direction. Notice it's a circle and we have our solid arrow pointing inward, indicating that oil comes into the actuator. The other one here is a bidirectional motor. So we got two arrows showing us that this motor can spin one way or the other. Down here we have our variable displacement bidirectional motor. Again, we just put a diagonal arrow across it and now it is a variable displacement. And just like pumps, sometimes they'll show the actual output shaft, the mechanical output shaft, and sometimes they won't. It's really up to the manufacturer and the type of schematic that it is. In terms of cylinders, there's many different types of cylinders out there in the industry. I'm just going to show kind of four basic ones that are quite popular that you will see. First off being double acting cylinder. What we mean by double acting is oil can be pushed into the bottom to extend the cylinder, and then we can push hydraulic oil into the top end to retract it. So we use oil pressure to extend and retract the cylinder. Unlike the single acting cylinder. A single acting cylinder, you only put oil into one end, primarily the rod or the base end, and that will extend the cylinder. In order to retract the cylinder, you have to connect the bottom here, the base end, back to reservoir or tank, and then rely either on a spring, like this cylinder is showing, it has a spring pushing it back, or gravity. So if it would be, for an example, on a combine feeder house, the feeder house, those cylinders are almost all single acting and they don't have springs. We just rely on the weight of the header or the feeder house to push the cylinder back down. So it's just gravity or spring return force. Another type of cylinder we see is telescopic cylinders. This one here is just being single acting again. The solid arrow here pushing oil into the base end, and it will push the whole cylinder up until the first section bottoms out, then it'll go to the next section, and then the final section, just telescoping as it goes out. This little arrow here on the top, notice it is an arrow, but it's not colored in. So solid arrows indicate hydraulic fluid. Hollow arrows are going to indicate gas. So in this case, air. That is a vent. So that's just showing a little vent line on the top, showing that air can go in and out of that chamber so it doesn't ever airlock or hydrolock inside there. So you'll see that a lot with pneumatic schematics as well. If you ever work a lot with pneumatic systems, on those schematics, their symbols look almost identical to hydraulic, but you'll notice all their arrows are hollow inside. Another type of cylinder out there is known as a balanced cylinder, also known as a double rod, because it has a rod out both sides. So whether you're moving this cylinder left or right, you have a rod going out either end, either retracting and or extending. So it is known as a balanced cylinder because we have the same displacement on either side of the rod. Whereas if we go back up to this double acting cylinder, this cylinder could also be called an unbalanced cylinder because it has a larger surface area on the bottom than on the top when we're looking at surface area of the piston, because the rod is taking up some surface area. So there's an imbalance or an unbalanced volume on either side as well. So this would be a balanced cylinder. Cylinders like the two examples up here would be unbalanced cylinders. So let's take a quick look at valves. Start going into valves. 4 common valves that are used a lot, that get confused a lot, mainly because they look very similar. So again, valves are squares, and we got different components and different sensing lines on all of these valves. So let's go through them one by one. The first one up here is going to be known as a relief valve. So as oil were to come in here, you can see if oil comes in on this line, it will just deadhead against the housing, because the arrow inside the valve is offset. It's not in the middle. So this would be a normally closed valve. So oil would have to come back, just deadhead here. If the pressure in this little pilot line were to build up enough to push this arrow against this spring, so whatever the spring is set at, if it's set at 1000 psi, once this pressure in this pilot line reached 1000 psi, it could successfully move this arrow down, allowing oil to flow through the relief valve, likely back to tank. So it's normally closed, and we are sensing the inlet of the valve. If we go over here, we can see our pressure reducing valve. Now, pressure reducing valve, you can see, is normally open. So oil will come in here and it just flows straight on through. But it has a pilot line after or on the outlet of the valve, pushing against a spring. So if this spring, let's say, is set at 1000 psi again, oil can freely flow through here, but once the outlet pressure of this valve reaches 1000 psi, the oil pressure can come around and it will now push this arrow away from the center, which would start to restrict the flow through the valve, creating an orifice, which would create a pressure drop. So this valve then would always maintain 1000 psi on its outlet. You would see this valve used a lot in transmission circuits, power shift transmissions. Power shift transmissions need roughly 300 to 400 psi of oil pressure at all times. So if you have a pump that's pressure is ranging anywhere from 500 up to 3000, you don't want your transmission clutch pressures to change. So you would use a pressure reducing valve that would be set to, say, 300. And then anytime this pressure, or anytime the inlet pressure tries to go above 300, or as it's fluctuating, this valve here will just self-regulate and always maintain 300 on the outlet of the valve. Two other valves that we got at the bottom. This one down here is a pressure compensated relief valve. So you can see this valve and the relief valve look almost identical. But if we look in the spring, there is a little dashed line. And if you remember from earlier, dashed lines are pilot lines. So what we mean by pressure compensated would mean if we have a pilot pressure coming into this line, it would actually assist the spring and add on to the spring. So if this relief valve spring is set, say, to 1000 psi, and we have a 500 psi oil pressure coming in on this line, the inlet pressure of the valve would have to build up to 1500 psi before it could open up. So depending on the circuit, we might want to change at what pressure this opens up. So it's pressure compensated, meaning that there is oil pressure coming from elsewhere to compensate or help out the spring. This last one down here is known as an unloading valve. Again, looks very similar to a relief valve. The only difference is it's not actually sensing the inlet pressure. It has a sensing line coming off from some other circuit. So an unloading valve is normally closed. Oil would just come up to the valve and just be deadheaded. However, if we have a oil pressure from another source that would come in on this pilot line and push this arrow against the spring and open this up, we could effectively dump all of the oil from this circuit off to tank. So we would be unloading this circuit on the inlet by using a different circuit to activate it. So this is what we would see with an unloading valve. Unloading valves are generally used when you have a fixed displacement pump used with closed center directional control valves, which, if you haven't taken it already, will be covered in another course. But this is what an unloading valve would likely look like on an ISO schematic.